Hi, I'm Ted Goldstein, structural engineer with Atlas Tube, and this month we're coming to you from the base of the George Washington Bridge. Now, when this bridge was built, they didn't have HSS, and they didn't have the HSS Connections Hub, but they did design a beautiful structure with a stiffening truss that has a whole lot of Chevron connections. So, in honor of this icon, this month we're going to take a look at the Chevron connection using the HSS Connections Hub. Let's dive in.
Okay, so here I have a very basic Chevron connection. I've gone with the bolted version here because there are a few more variables that we get to play with, but there is also a welded version where the braces are getting welded directly to the gusset. And I want to take this opportunity to show a few new features that we have here, both for this connection and for the connection hub as a whole. So in the original version of this connection, there was very limited ability to change the geometry of the bolted connection, but now we have the number of bolt rows and bolts per row, and then also the spacing are all variables that can be controlled by the user, so a lot more flexibility there. Another big change, which we're going to make use of here, is in the load inputs. So in all previous calculations, you used to have to put the individual load cases, dead live, etc., in for the calculation. We got a lot of requests to make it possible to just input the factored load, because often those load cases, or rather the governing combination, is already known. So now we can do that. We've got the factored load here. Let's go and put 150 kips, and that's going to be compression in one brace and tension in the other. And not surprisingly, for this relatively small connection here, we've got quite a bit of overstress. We're at 410%. So let's, use all the levers we have at our disposal and try to get that down to something that works. So good place to start is actually, first we can see the gusset plate is at 400%. Now we don't need to get that down to below 100 quite yet, because the bolts are going to have an effect. But clearly we're going to have to give that a little more capacity. So let's start by increasing the thickness of the gusset plate. It's at 3/8. Let's go to 3/4. I think right away we're going to see a pretty big difference. So now we've still got a lot of red, but now we've got the bolts are governing. So let's go ahead and take care of those, because actually changes we make to the geometry of the bolt group may help some of the other capacities as well, or help some of the other limit states as well. So we're at 210%. Now we can right away go ahead and change from 2 rows with 2 bolts each to 3 and 3. And not surprisingly, that gets us down to about 93%. Now that's with 3/4. If we wanted instead to do 7/8, maybe we could do 4 rows with 2 bolts per row, and that works as well. Now we're going to have to check here if we have, we went the long way. I meant to go the opposite way, so let's go ahead and switch that, 2 and 4. And when we do that, we can see now we have a lot of alerts here, and that's because our plate is not wide enough for 4 bolts. But as I say, we now have a lot of freedom when it comes to the geometry. So let's just go ahead and go to the splice plate. You can see we've got some red here because it's not wide enough. So for 4 bolts, if we make it 12 inches wide, there we go. Now we have enough space. It's reflected in our diagram, and we're down to 159%. And now the governing capacity is the splice plate. That's the only thing in red. Some people might call this a knife plate because it's the piece that cuts into the end of the HSS. Here we're calling it the splice plate. So let's go down there. Of course, it's only 3/8 of an inch thick, so not surprising that it's overstressed. So let's go ahead and put this to 3/4 of an inch as well. Now we're down to 101, but an interesting thing has happened. The splice plate is okay. It's no longer governing. The gusset plate is now overstressed, even though it had previously been okay. So why is that happening? Well, if we come down here to the calculation section, and we can find the overstressed at the gusset plate capacity and open that drop down. We're okay on block shear, okay on tensile yielding, compression, but we fail in the compression, bending compression interaction. Now, what is that? If we drop down here, of course, as with everything on the Connections Hub, we always can just click on something to get an explanation. And we can see what's being measured here is the bending that's induced from the fact that the gusset plate and the splice plate are not actually coaxial, right? They're laid against each other, and so there's a moment induced from that axial load. So when we went ahead and made the splice plate thicker, that actually increased the eccentricity, and it caused the gusset plate to be overstressed. So we could, of course, just make the gusset plate thicker. It's already 3/4 of an inch, which is pretty substantial. So rather than doing that, we can see if we look at the splice plate capacity, we actually have a little bit of leeway here. So I'm going to reduce the splice plate thickness from 3/4 of an inch to 5/8 of an inch. And you can see when we do that, the demand on the gusset plate goes down. And that's because, again, we've reduced that eccentricity due to the fact that those plates are not coaxial. And we still have just enough for the splice plate itself. So a lot of different variables that we can play with to get these connections to work. This is a relatively small one with a relatively small load. Of course, we could do much bigger connections, even up into the jumbo HSS sizes. But really, this is a calculator that started off, the original versions were pretty basic. We've been adding a lot of tools and a lot of functionality to it, and we'll, of course, continue to do so. It's pretty simple once you know how things are interacting. So really appreciate you joining us this week, and look forward to seeing you next month on the Connection of the Month.